Hello everybody, and welcome back to the first video in a series of 2 videos for the Biostats exam. In this video we're going to be covering all the major topics from exam 2. I will say exam 2 looks to be a lot less math heavy than exam 1 was, and exam 1 didn't even have that much math in the end, despite the 30 or so equations he gave us on the equation sheet. So hopefully this 1 goes a little bit faster and 2 is a little bit easier. But what I want to talk about is the Bonferroni correction, F-test, ANOVAs, and all the variations like MANOVAs, ANCOVAs, correlation, simple and multiple linear regression. I think that's going to be a really big topic in this video. And just also some like little random miscellaneous tests and variables. And then in the next video, I should be covering non-parametric tests. So if you're looking for that, I would look for the next video, which should be released on Tuesday the 17th, I believe it will be. So t-tests are what we've been using up until now, and t-tests are a pretty good test. However, the limitation of a t-test is that it can only be used to kind of compare 2 samples to each other, 2 groups to each other, which is fine if you need a direct comparison, but not fine if you are comparing multiple groups, because I feel like a lot of the times we're comparing more than 2 sample groups, unless it's for a really simple beginning study. So what can we do about that? There's 2 things. The first thing we can do is the Bonferroni correction. This is not ideal. This is not preferential. This makes it very hard to get statistical significance. All the Bonferroni correction is you're still doing the same things as a t-test. You're comparing all your t-tests to each other. Like let's say if you have 3 groups, you'll compare group 1 to group 2, group 1 to group 3, and group 2 to group 3. And those are called your number of comparisons, essentially. Now, how do we adjust for this in terms of the p-value? Essentially, let's say we have a p-value of 0.05. For the 3 samples I just described, there were 3 comparisons, if you recall, the ones I just listed. So you're essentially just dividing that p-value by 3 for those numbers of comparisons. If you had 4 groups, it'd be 6 comparisons, and then we'll just go up additively. And then technically, we're kind of always doing a Bonferroni correction because 2 groups are just divided by 1, so our p-value stays the same. So you can think of the Bonferroni correction as something that's always there, just never really thought about in most cases because we don't need to for like standard t-test. But if we were to divide that 0.05 by 3, we'd get something like 0.0167, which is obviously a lot smaller of a p-value. It's much harder to gain significance this way, and it's also just very tedious. So we're not really ever going to use this. What we'll do instead is we'll do something called F-test. The basic idea behind an F-test is we're essentially comparing variance within groups and between groups. So what does that mean? So variance between groups, well, I guess technically the equation for it includes the mean between groups, but variance is obviously going to shift that mean. If there's high variance between groups, right, that would mean we have differences between the groups, which is what we want. That would indicate statistical significance. The reason why variance within groups is in the denominator, however, or mean within groups, is because if our groups aren't super uniform to begin with, it makes our test weaker, right? So even if our groups are super different from each other, our control groups, if the variables within groups are different, it makes it a lot less likely that there actually is a difference, because essentially these groups could be completely random in where they're settling. So that's essentially the idea behind an F-test, and it's just the simple division equation, mean squared between over mean squared within. We use something similar in ANOVA, but just for a simple F-test, this is all we need. Our null hypothesis for an F-test is just that our means for all of our samples are the same. Kind of makes sense, right? If our means are the same, the groups aren't different, and then they stay standardized. And then H1 is just the opposite. Not all the means are equal. This means there is significance between at least one of them. And that's another thing. There may not be variance between all the groups, but there may be variance between some of the groups. And that's what the F-test does. So even with this, it could be a little tedious because we need to compare all those individual groups. But with that, we can kind of see which groups actually are significant. The way that we get our critical value is there's 2 things we need to do. We have V1 and V2, so let's just say our F critical requires V1, V2. V1 is K minus 1, and K is our number of treatment groups. This is kind of what we talked about for the Bonferroni correction. This is one of the few mathematical derivations we'll probably need to make for this exam, and we'll never need to use an F table. I will show a little more of this math on detail in the next slide. But essentially, right, this is like our 3 number of groups, our 3 number of conditions. So in this case, K equals 3. But you can see that our degree of freedom, our first one, this is V1 as well. It's K minus 1. So our V1 is actually equal to 2. V2 is a little more complicated. It's N, our total number of samples, minus K. So K we just established was 3. N obviously varies from experiment to experiment. I believe the example I show has 3 groups of 15 samples. So in this case, N would equal 45. And again, I'll show this on the next slide. So if we do 45 minus 3, then we get 42. So V2 equals 42. So then our F would be like, that's an F, don't worry about it, 242. And then we could just find that from an F table. So that's how we get our V values. And again, I might show that a little more in detail on the next slide, just to reinforce that. And then essentially what we're looking for is we'll need our grand mean, our mean squared between, and our mean squared within. Just for F alone, we only need mean squared between and mean squared within. But on the next slide, I'll show you when we can use a grand mean as well. Okay, so this will probably be the most complex math we have to do on the exam. Honestly, we probably won't even get a full problem like this, but I do want to talk about it. For manually calculating an F value, it's kind of tedious, right? This is for like a one-way F test that we'd have to do something like this. So F is equal to your mean squared between over your mean squared within. How do we do that? So to get our mean squared between, we have this equation, the sum of our number of samples times the square difference of our sample mean and our grand mean divided by our number of groups minus 1. Mean squared within is our number of samples minus 1 times the standard deviation of each sample divided by our total number of samples minus our number of treatment groups. So really the only thing we don't immediately have access to from all that is our grand mean. Now what's a grand mean? A grand mean is, well, each one of these treatment groups has a mean. For this one, it's 26.26, or, wow, I don't know how I butchered that, 276.26. This one, 275.29, and then 273.7. Grand mean is different. It's like a weighted mean. In this case, we actually don't need to worry that much about it. We can just average these 3 numbers without weighting them. But if these sample sizes were different, like let's say one of these groups only had 10 samples, it would have less of a weight. This is just like a weighted averages problem. I think I have one in my first video in case you don't know how to do that. There's also a problem like it on the first exam. Just basically, a simple way to do it is like, if you know your total number of samples, so let's say this one is 10 and these other 2 are 15. I'm going to like round these numbers to make my life easier. So it'd be like 273 times 15 plus 275 times 15 plus 268 times 10 over total number of samples, 15 plus 15, 30, 30 plus 10, 40. And this is how you do a weighted mean. This is how you do a grand mean. But luckily for us, our sample sizes are the same, so we don't need to do that step. And literally, we can just take an average of these 3 numbers. So I'm going to do that in my calculator really quick. We have 276.26 plus 275.29 plus 273.7. Divide all that by 3 to take the average. Our average or grand mean is 275.08. So now for the tedious part of the equation. So we're going to be using this equation. So I'm going to be substituting things in because I don't feel like writing this twice. So I'll write slow though, and I'll explain what everything is. So just follow along. So we're adding all these things. We have 15, which is our n, times our xk minus our grand mean. So our first xk is 276.26. 276.26 minus grand mean 275.08 squared. We're looking for a square difference. And then we'll add 15 times our next xk, 275.29. 275.29 minus 275.08 squared, plus again our final one, 15, number of samples again, 273.7, and we're not using this 10 anymore, by the way, if that wasn't clear. That was just for the other example. Minus 275.08 squared divided all of this by k minus 1. If you remember, k is our number of groups, so we have 1, 2, 3 groups, 3 minus 1 over 2. Let me plug this in my calculator really quick. No, man, this is so much. 276. I'm going to round these numbers. They're not going to be exactly right. You shouldn't round on an exam, but I'm going to do it for the sake of time. It's 275 squared plus 275 minus 275 squared plus 274 minus 275 squared divided by 2. We get like 15. Again, not an exact number, but I don't feel like getting the exact number. If you'd like, this is all the math you'd need to plug into your calculator to get the real value. You can tell me in the comments what the real value is if you'd like. I'm just not going to bother with that. Next up, we need the mean squared within. So this was, I should have written like an equal sign. This was mean squared between. Mean squared within is a little easier because it's just, it's another like summation. It's our samples minus 1. So it's 15 minus 1. I'm going to write that as 14 from now on, times our standard deviation 1. This is 3.27, standard deviation 1, plus 14, again, samples minus 1 times 3.46, plus samples minus 1, 14, times 4.16 for that last standard deviation. And then this one is our total number of samples minus k, actually, is what's in the denominator. So our total number of samples, we can add them. So it's like just 15 times 3. So, 3 conditions, 15 for each. That's 45 minus k, which 3 groups? 3. So this is actually 42. And then let me put this in my calculator really quick. So we have 14 times 3.27 plus 14 times 3.46 plus 14 times 4.16. Divide all that by 42. We get 3.63. So now what we need to do, it's final step, mean squared between divided by mean squared within. 15 divided by 3.63. 3.63 equals 4.13. And we have our F critical value. If you remember, there's two values, right? There's V1, there's V2. We did talk about this on the previous slide. V1 is K minus 1. So remember that K is our number of groups, so 3 minus 1 is 2. That's how you get this 2 right here. It's right there. I don't want to circle it because it's going to cross it out. It's so small. And then we also have our V2, which is N minus K. So we just calculated N, 45 minus 3 is 42. 42 for the other value. You can get that from an F table. We probably won't need to read an F table in the test, so don't worry about that. And with that, we get an F critical value of 3.23. And this is our F observed. So since our F observed is greater than our critical value, we can reject our null hypothesis. We can do our alternative hypothesis, meaning that this data do have significant differences between each other. Again, I don't remember if this value is actually significant before I shortcutted this part of the problem, the mean squared between. So it could not be significant in his notes, but just for the way I did it, where I rounded my numbers, it is. So just in case that wasn't clear, in case you go back and look at that as well. If you wanted to calculate the actual value and see, it's the exact same process, just don't round your numbers. The last thing I want to talk about is sum of squares within and sum of squares between. I put the equations for these two. We're never going to need to know these. He's going to give us these on an exam. At least I would be pretty confident he would. But something that he might give us is he might ask us to reference this equation. The sum of squares total equals the sum of squares between plus the sum of squares within. Now, he might just give us these two and have us find the sum of squares total, which would be fine. I think what's more likely, though, is he has us solve for something like sum of squares within equals sum of squares total minus sum of squares between, or sum of squares between equals sum of squares total minus sum of squares within. I don't have any numbers for that. It's just addition and subtraction. It's not too hard. Don't overthink it. But we probably do get a problem like that because he did reference that a couple times in class, so I wouldn't be surprised. But with that, I think that's pretty much everything I wanted to cover as far as one-way ANOVA goes. So now that we've done one-way ANOVA, let's talk about two-way ANOVA, or two-factor ANOVA, either one. This is slightly more complicated mathematically and conceptually than one-way ANOVA, but for the purposes of our test, it's actually probably going to be easier. Just for the fact we're almost certainly going to get a table like this, and we're going to have to fill it in. I would assume we see something like this in the test. It's also in the homework. So let's talk about what a two-factor ANOVA is. A two-factor ANOVA is essentially comparing two independent variables at once. And for this, we have three hypotheses. In this experiment, we have a drug company that's giving two formulations of drug, formulation A and formulation B. They're also varying the order that these drugs are administered in. So we have formulation A is given before formulation B, and formulation B is given before formulation A. And we're looking at the mean effects of each. So we essentially have four conditions, these four boxes right here. 1, 2, 3, 4. So what would our null hypothesis look like then? We'd have 3, and we'd have an F value for each one that we'd have to either find is significant or insignificant. So for the first one, the hypothesis is, and this doesn't really matter the order of these, the order 1 and order 2, the administration order are equal, so they don't really matter. They don't have a significant effect on the drug effect. The next one is that the mean effect of formula A is equal to formula B. The formula themselves are like equivalent. There isn't a big effect between the two. And then finally is what we call the interaction effect. This is that it essentially combines them. It's that interaction of formulas and interaction of orders, I think I just circled those in reverse order, do not have a significant effect at all. So, or well, they might have some at certain p-values, but not at the ones we're looking at. And for these, we do a similar thing that we've been doing, where we calculate a V1 and V2 based on sample sizes and number of conditions. For this, we actually have the p-value of 0.05 being 3.99 across the board. It makes our lives a little bit easier for this. So we'll know the value we're shooting for each F value. And then something else I gave us here, because I blacked out some of the rows in this table because I want to show you how to solve for them, is I gave us the number of participants. So degrees of freedom total is probably the easiest thing to start with, because degrees of freedom total, we'll do DOF total, is just number of subjects minus 1. In this case, subjects are participants. There are 72. So 72 minus 1 is 71. Boom. First box done. The next easiest thing to do is probably the degrees of freedom between, which in this case, Dr. Guo put order. Again, this doesn't really matter. This will be our J value, and degrees of order, the formula, essentially. This is also between, sorry. And this will be our K value. These are simply the number of conditions for each. So for our rows, we have 1, 2 rows. And in order to find the degrees of freedom of a row, we would do J minus 1, so 2 minus 1. This would be 1 degree of freedom. Same with this, K minus 1, so that's 2 minus 1 is also 1. The reason I blanked out this box and not this box is because I wanted to show you something. In order to get your essentially sum of squares, if you aren't given it, but you are given the degrees of freedom in the mean square, all you have to do is to divide mean square by your degree of freedom So mean square over df equals sum square. So in this case, our sum of squares for the formula is 1092.5. The interaction effect, the variable, you actually solve it for, it's your j minus 1 times k minus 1, which in this case is also just 1. Again, a similar thing is if you have your degree of freedom, you can simply you can multiply that through, or divide this by this to get this. If we don't have it, in this case I just gave it to make life a little bit easier. There's two ways to get this next value. I'll show you the way that's probably going to be in our exam, but you could also just simply find out what 23,000 or 2369 is by dividing it by 34.84. I'll just show you how to do both ways. So the traditional formula to get this is n minus j times k. So in this case, we know our n. It's 72. So we have 72 minus, remember j and k aren't 1. J minus 1 and k minus 1 are 1. So this is actually minus 2 times 2 is 68. So we have 68, and then I'll confirm really quick in my calculator that 34.84 times 68 is equivalent to the, 2369. So again, just both ways, whatever you're more comfortable with is honestly fine. This last value might not always be given. This means error, the mean square error, which is it's very important because we need this to calculate every f value. For an f value, it's essentially our it's a mean square error divided by sorry about that, my recording cut out. So the way that we get our f value is that we do our mean squared divided by our error within. So we have to do that for each of these, get an independent f value for each. So we'll do 1.02 divided by 34.84. With that, we get a value of 0.03. And remember, this is an f value. This isn't a p value because we want our f value to be greater than 3.99. So this is actually really insignificant. We'll also do our 3.52 divided by 34.84. This is just 0.1. Again, not significant at all. When we do our 1092.92 divided by 34.84, however, we get an f value of 31.7. Or 0.4, I'm sorry, which is pretty significant, right? That's 10 times the value of our f value for hypothesis 2. So in this case, actually, we have one f that's significant, and that'll be our, in this case, our formulation effect. So the formulations have significance between each other, but the order you give them in the interaction between order and formula have no significant effect. So now let's talk about another two models that are similar to ANOVA, but not quite the same. The first one we probably won't be tested on very heavily. It's MANOVA. And essentially what MANOVA is it's special because you're not only testing for multiple independent variables, kind of like where we were with two-factor ANOVAs, with the different formulations and the different orders. Those were multiple independent variables, and we could have had more. We could have had 3, 4, 5, just would have taken a lot longer. But as well as those, we also have multiple dependent variables. So you can see how this gets complex a little bit quick because we're not only texting, like let's say we're doing a drug, right? We're doing formulation order. Let's say we want to look at blood pressure, but we also want to look at heart rate, and we also want to look at long-term life expectancy outcome. We can do that with a MANOVA. Again, it's just very tedious and complicated and kind of above the level of stats we need for this class. At least math-wise. So just be aware that MANOVA is like multivariable. That's even multivariate's the name, if that helps you remember. ANCOVA we might be tested on a little bit, just for the fact that this is so similar to multivariable regression. But so I want to explain the key difference here because this will probably be a question on this exam that's coming up. Essentially, we have multiple variables uh, and a single dependent variable. So this again is more similar to like regular two-factor ANOVA, right? We have these multiple variables and a dependent variable. What we're looking at, though, is what we'll get to on the next few slides, is we're actually looking at the Pearson correlation coefficient as well, this part of the equation. Or it might not be Pearson, it could potentially be something else. Pearson will traditionally be what you use, though. But even though you're looking at that correlation, you're looking at correlation between the independent values and not the independent and the dependent. That's how this varies from multiple linear regression. Multiple linear regression is modeling correlation between the independent and dependent. This is looking at correlation between the independent and then also some effect on the dependent. But the dependent is not the main thing that's being looked at in these. And then what this kind of looks like in the form of a research paper, in case we get a question like this, is individual factors may not be correlated per se. These are p-values. We'll learn about r-values, which again, we might have mentioned again in a different part of the video. I don't think we have yet. I record these slides out of order sometimes. So as you know, a p-value that's greater than 0.05 is not significant. So just the time variable is 0.969 here. So this isn't significant alone. However, when we have time in school-based healthcare, along with time in school-based or time in race for this study, we actually see 0.044 and 0.023. These two are significant. So this shows that the interaction of these two variables actually have some significance together. There's a correlation there. So that's like kind of an application of an ANCOVA. So if you get a question like this on the exam, the answer is probably ANCOVA. And it's just being able to, if the table lists multiple variables together that have different p-values, and remember, p-values, not r-values, because that's another big difference between linear regression and this. Linear regression will have r-values, ANCOVA will have p-values or f-values. So that's another way to distinguish that. So that's how I would keep them straight in my head. So now we're talking about correlation. I've alluded to it quite a bit throughout the rest of this video. Correlation can be used for all types of data. It can be used for nominal, it can be used for ordinal, and it can be used for interval as ratio. But what we want to look at least to begin with, is what's called Pearson correlation. And this is little r. And this is only for interval and ratio data. Interval and ratio. So what is correlation? So correlation is essentially how much our data responds to a standardized model, or how much our dependent variable changes in response to a change in our independent variable. So in this, we're changing our independent variable, right? Which is kind of what we've been learning for years. You change the thing on the x-axis and see how the thing on the y-axis responds. Something that has a good correlation, it'll be close to what is called a line of best fit, or a regression line. So you can see, I don't know how well you can see, they're kind of dull, all these little dots around this line. This is a pretty good regression model. This has some pretty high correlation because it fits our model well. This, on the other hand, we could estimate a line. I don't know, probably be something like this. It'd probably be similar. But look at this. Our data is so far apart from that line. It's all over the place. So even though the slope may be similar, and even the equation of the line may be similar, the correlation itself is not. I would memorize these values down here, essentially what they mean. And so if it's less than 0.2, it's a very weak correlation. There is some correlation. That would probably be a graph like this, just weak. 0.2 to 0.4 is weak. 0.4 to 0.7 is moderate. 0.7 to 0.9 is strong. That would probably look like this graph, where the, and again, I'm just eyeballing these. I actually have no idea. These would correlate because our data points are so close to our regression model. And then ideally what we want is we want very strong correlation, because this shows there's a high correlation between our testing condition and our control condition. So why can correlation error kind of occur in the first place? Like, why might something not have perfect correlation, even if it is one-to-one? Like, let's say we have a drug that directly increases blood pressure. Why will data points be all over the place, potentially? Even if we know that on average in 99% of people, it's going to increase blood pressure by 5. Um, there could just be an error in measurement. We could be measuring the blood pressure incorrectly. The person administering the experiment might have read the cuff wrong. You could switch up your data. Don't do that, but you could. If you weren't paying attention, you could accidentally write something under the wrong area. Just random variability among people. This could be genetic. This could be due to age. There's a ton of things. Uh, Too small of a sample size is really important. If your sample size is larger, your correlation, if there is one, is generally going to be a lot stronger. Um, and then also something we'll talk about later are multiple collinearity. That's essentially volume, or some variables are too similar. Like weight and height are so proportional to each other that if we're measuring like both, they might throw off an experiment. If we're doing a multiple linear regression analysis. For single linear regression, we're only measuring one dependent variable against one independent variable. Um, these next kind of tests are for nominal and ordinal data. Kendall specifically is just ordinal, and it's also for very low sample sizes. That's when this works best. Spearman, on the other hand, can be nominal or ordinal. And something to note about both of these is these are non-parametric tests. So what does non-parametric mean? Because I know we were asked in the last exam, and I don't know how well I covered it in my last video. So I'll explain it here just to make sure everything's covered. Non-parametric means the distribution is not normal. So in a parametric test, right, we have our normal distribution curve, z-test, t-test, all these things, even a-test or ANOVAs and f-tests are going to be parametric. Non-parametric, you can see the distribution. I guess this is a distribution. This is more of like where the data falls, but you can see more of our data kind of like there's more outliers, so I don't know exactly what this graph would look like, but it wouldn't look like this if we were plotting frequency, essentially. Um, so those are just two other types. Know that Kendall is just ordinal for low sample sizes. Know that Spearman is just nominal or ordinal. These will be part of our non-parametric video. I don't know how much he's going to want us to cover them because I have not recorded that yet because we haven't learned it yet. So if I explain it more in depth in that video, go with what I say in the second video as opposed to this first video. So how do you actually calculate an R value? Going back to our linear regression. Um, Realistically, we won't have to calculate this because this is a very obnoxious equation. Here's how you would do it. If you want to go ahead and take the time to memorize that, go ahead. I'm not going to personally because at that point I think I'm just taking the L. But here it is, just in case. So what does all that mean? Essentially what this equation means is it's finding the distance of each individual point away from a line we create. So it's like this line of regression isn't obviously, it's got to come from somewhere. And we can kind of generate that from this equation, and we can find out how good it is based on how far away the data points are using this math, which I can't even pretend like I know how to explain that mathematically. So I'll just move on to the hypotheses. So for Pearson, our null hypothesis is always r equals 0, right? And this makes sense because if it's less than or equal to that 0.2, very weak correlation, essentially nothing. We will have an r critical value that we can calculate each time. So r doesn't technically have to equal 0. R could equal like 0.2. It really depends for how strong we need our experiment to be. But basically, r is just less than the r critical value. Or r observed is less than the r critical value, which is kind of the case for like all of our tests, right? Like that's the same for t-test, that's the same for z-test, that's the same for f-test. Nothing really new there. Alternative is that your r is kind of greater than the threshold. It does not equal 0, so this would be something like r equals 0.8. Like that's a pretty good correlation value. Oh, and that's another thing. Correlation only goes from 0 to 1, if that wasn't clear from this table. Just something to mention. So if you ever get an r value that's more than 1, and these can also be negative, so plus or minus. Yeah, it's probably wrong. In fact, it's definitely wrong. So I would redo your math. The degrees of freedom for an r test are always number of samples minus 2. So this is a little different for other ones. They've always been n minus 1 up until this point, but now it's n minus 2. See that right here. So if you have like 6 samples, let's say 6 minus 2 equals 4. We have 4 degrees of freedom. And with that, you can find the R critical with your degrees of freedom. And for the a sample in the book is, I think I'll explain this a little more with multivariate. We don't exactly need to do the math of this because that would obviously require us to calculate an R value from this equation. But if you have an R critical that is less than your R observed, and this equation is R observed up here, then you have significance because you're closer to that threshold of 1, a really strong correlation. All right, now let's talk about some random stuff in regards to simple linear. You've probably all heard the phrase before that correlation does not equal causation. Essentially, if two things are related, that does not mean one causes the other in simpler terms. Let me show you when it does. So basically, there are 3 conditions that must be met, and I would guarantee this is like a select all that applies, or all of the above on the exam. I would be shocked if it wasn't. The first one is that X precedes Y. So let's say in the case of like we're giving a drug to lower blood pressure, we need to give the drug first before blood pressure lowers, right? Kind of common sense, but something I think we take for granted sometimes. The next one is the effect only occurs in the presence of X. So if X is our drug, blood pressure will only lower or only be lower in patients if they're given the drug. It's not just like a random time of day. These people's blood pressure just happens to lower. Like maybe while they're asleep or something, and that's when we were taking the sample. Like, right, they need to have the drug in order to show a causation. And then finally, it's very similar to 2. There's no effect in the absence of X. Kind of the same thing. But, you know, again, it's sort of just like the exact opposite, but saying the same thing, like a double negative, I guess. Um, and I might have even just said 2 is 3, to be honest. So it's like the blood pressure will stay the same if there's no X or no drug. So that's kind of all that's needed for causation. Again, pretty common sense stuff, but I guarantee that gets copy paste and put on the exam. So definitely know that. Um, Next up, let's talk about correlation matrices. These are really nice, actually. This is for looking at correlation between multiple variables. So for example, there's a correlation between height and weight. This also goes back to a critical value that was already calculated. This probably goes back to our sample size of 6 because this is like the same one that was on the previous slide. So you can see height and weight have a positive correlation. I have no idea what area under the curve means in comparison to weight, but it definitely correlates because that's bigger than our 0.811. And then height and area under the curve also do as well. Again, no idea what area under the curve is measuring. Maybe that's like, yeah, I can't even warrant a guess on that. But anyways, they're correlated. And that's simply because these numbers are, well, actually, this one isn't. I don't know why Dr. Guo bolded this one. Yeah, so this one is not, because this is not bigger than 0.811, so don't worry about that. Yeah, so now let's talk about canonical correlation. This is confusing. This is kind of like a MANOVA in the sense that we have multiple independent and dependent variables, except this is sort of like how multiple linear regression relates to ANCOVA. This is how canonical correlation is kind of like the equivalent for MANOVA. Because if you remember, multiple linear regression only measures it measures relationship between the independent and dependent variables, where ANCOVA does have independent and dependent variable, but it's more looking for the correlation between the independent variables. This is MANOVA only looks at the correlation between the independent variables, but it also has multiple independent variables. Or I'm sorry, I said that backwards. Basically, all you need to know with this one, I'm making this way more complicated than it needs to be. This was one slide in his PowerPoint. You're looking at correlation between multiple dependents and multiple independents. So it's kind of like we're doing correlation studies between each, whereas MANOVA would only do correlation studies between the independents, even though it would have multiple dependent variables as well. Sorry if that was confusing. I honestly doubt we even get a question on that on the exam. But if we do, just know multiple dependent variables, multiple independent variables, correlation between all of them. Now let's talk about kind of when it's appropriate to use a regression model or a linear regression model. Um, for these four graphs up here, um, this first one is fine, right? Like there's data all around it. It's pretty close to the line. It's fine. This one right here, you can see that the line would kind of be more like this, a little bit shallower of a slope, if not for this outlier, which kind of messes this model up a little bit. I would say if that outlier was statistically far out enough, you could probably throw it out in an experiment. In this case, I have no idea whether it is or not, so it's kind of messing up that model a little bit. However, this is still pretty close. It's still pretty appropriate, so it's fine. This you can see, number two, it's more of like a quadratic curve. You would not want to use linear regression for this because even though you could create a line of best fit to this, um, there would be no reason to, right? Because you can already see a different pattern emerging, so you'd have to use some kind of different test. What that would be, I have no idea. We don't need to know it for the exam, so unless I somehow figure it out in the next part of the video, in which case take my word from there. This last one, right? These almost look vertical. They wouldn't be vertical because you can kind of see they're spaced out. This is honestly a problem with the scale of this graph. If this graph was scaled in a little bit, I think you could make an argument for using regression like this. However, if you're trying to measure your data all the way out here, and this is what your regression looks like, you're just not gonna, it's just not a good model. So these two and four, would not be good candidates for linear regression. 1 and 3 are fine. 1's definitely better than 3, but it's not the end of the world. Now let's talk about R squared. So R squared, essentially, and this will be a question. He said this in class, so I would remember this. It's the proportion of variance in Y. So this is how our dependent variable will vary. That can be predicted by the independent variable, or predicted by X. So essentially, right, when we're measuring, we talked on the previous slide about how there can be variance in like measurements or variance in data due to like researcher error. Uh, and that would all affect X. Our final result would affect Y. But essentially, this our R squared is measured as a percent actually, which is just R squared is exactly how you think you get it. It's your Pearson coefficient squared times 100% to make it a percent. So let's say we have an R squared of 0.8. If we multiply that by 100, we get 80%. This means that any variance in the dependent variable, so on our y-axis, is accounted for by x, which really means about like a 20%, I don't want to call it error because it's not exactly like error, but 20% error in dependent variables is unexplained. But 80% is already explained by our variance in x, which is pretty good. Similar to how we had our correlations for our just Pearson coefficient, uh, bigger R squareds are generally better. In fact, always better, just for explaining your data. And just knowing this percent rule and just explaining how much variance an independent variable causes the dependent variable. So for a graph up here like 2, let's just say this has like an R squared of 99%, like a really, really good R squared, right? That would be like an R value of like 0.995 or something. This point right here, this outlier, this could just be something wrong with one of our independent variables, something down here along this axis. So with an R squared like that, we could just be like, yeah, this outlier is here, but it's explained. You know, kind of makes sense. However, if this R squared was something like 10%, this might actually be a value and something we need to consider our model and see, oh, maybe there's something else going on here. So if we have a low R squared and we do have outliers like that, we can reconsider maybe taking some more samples, maybe choosing a different experimental design because something isn't working. This is an equation right here. I doubt we'll ever need to solve it. it's called adjusted r squared. We might be given it. If we're given both r squared and adjusted r squared, always use adjusted. It's just a little more accurate. The reason why it's more accurate is because it takes into account your number of samples and also your number of independent variables. For a simple linear regression, this is always just 1. So essentially, if it is simple linear, p and -1 will just cancel out. Or actually, no, sorry, I'm lying. Since these are both subtraction, it'll be n-2 in your denominator. Right, because if p is 1, it's like n-1 minus 1, n-2. And then we also have n up here in the numerator. So since it takes into account that sample size, it's more accurate. So for small sample sizes, this would be less accurate. For bigger ones, it has less of an effect. And then for something like multiple regression, p might not be 1. P could be 2, p could be 3, p could really be anything. But again, I don't think we'll ever have to calculate adjusted r squared, so don't worry too much about it. Okay, so now that we've gone over everything in simple linear regression, let's talk about multiple regression. The only difference is simple linear regression will only have one independent variable, right? If we're doing like a drug dose effect change in blood pressure, that'll be it. Versus multiple linear regression, we will have, let's say x1 is still drug dose. Let's say x2 is like drug. These need to be continuous variables, so I was going to say formulation, but that's not really continuous. So something like drug administration time, I guess, if it's like an IV dose. Yeah, and this can be honestly like an infinite number of things. It doesn't really matter. We also have these b variables. In our last equation, b was kind of just the slope of the line, right? And b naught or b0 was our y-intercept. Here we still have our y-intercept. This is just a constant. However, each of these b's is different. And where do we get them from? These are our beta values. And what they kind of represent is strength they contribute to the slope. So if it's bigger, it'll have a bigger influence on the slope. And that can be, and when I say bigger, I don't necessarily mean like higher value positively, I mean higher absolute value. So you can see here in this table, or maybe you can't because it's really small. I don't know why I copied this small. We have like negative 0.119 and negative, I think that's 0.863. So even though, yeah, negative 0.119 is technically bigger, negative 0.863 has a higher absolute value. So this will contribute more to the overall slope of regression. The example I pulled for this is there's two variables. We have female life expectancy versus fertility, and that's measured by average number of children. This was taken from data from I think like 85 countries is what I said in class. And then also infant mortality versus female life expectancy. So you can see here, if we're going to make rough lines of these, in a multiple linear regression, these lines would kind of be like averaged, is how this would work. But you can see here that this infant mortality, even though it has a steeper slope, which is important, that's not what's contributing to the b here. What's contributing to the b value and making it like have more weight in multiple linear regression is actually the fact that the r value of this line is going to be greater, right? Because think back to single linear regression. All these dots right here are so much closer to this line than over here. So if the dots are closer to a line, that means your b value is higher. It's not the slope of the line. They might be related in this case because this one not only has a steeper slope, but it also has a higher r value. But that could be flipped. So just remember that it's your r value that's going to determine your beta value or your b value. Again, these have r squares as well, just to show how much variance is there. We kind of talked about that on the previous slide. It's really no different here. Something else that could be used, this is a little more rare. It's called a standardized beta, or b coefficient. And essentially it's your small b over the standard deviation of x and standard deviation of y. Nobody uses this. It's much easier just to generate a b value for each of your conditions. But you can. If there's a question on that, this is what a standardized coefficient is. That's really all I have to say about it. I just wanted to throw it in here so the video is comprehensive. Something else that this isn't unique to multiple regression per se, In fact, this wouldn't be used in multiple regression, but this is just the order it came in the PowerPoint, so this is the order I put it in, is something called dummy variables. Dummy variables are nominal data, and they're nominal data with only two values. So in this case, you can see male and female. It could be left-handed or right-handed. It could be you prefer red over preferring blue, anything like that. And then it's assigned an arbitrary value. It's assigned like a 1 or a 0, kind of like these binary values. It doesn't really matter which one is which, because essentially, like, if your value is lower, that means there's more values with 0. And if your value is higher, that means there's more values with 1. So again, it's just like in this case, they gave male 1, female 0. You could flip that and do the exact same thing. But for example, if your value is 0.128, it probably means there's more females, right, in this study, because like an even amount of males and females would be 0.5. But since it's closer to 0, which is close to the female value, it means there's like disproportionately more women in this study. Next up, just an experimental design thing. This is for multiple linear regression. Multiple linear regression. This is how many samples you need. For each independent variable, you need 15 subjects. Otherwise, your study is just bad. So for example, if you have two independent variables, like we had up here for this example, the fertility and the infant mortality, we would need 30 samples, which you can see here. I think there was like 85 countries, so that's like 85 samples. They're totally in the clear with that. This is just a minimum. This isn't obviously like your max cutoff. More data is always better. If you had 4 independent variables, you need 60, 15 times x, not too crazy. Something else is called the problem of multiple collinearity. We alluded to this in a previous slide. Essentially what this is talking about is if two variables are related, right? Like height and weight. If you are taller, you are probably going to weigh more. If you weigh more, statistically on average, you are probably taller, right? Like those two things are related because they're both relating to body size. Because like if you're taller, you have more body mass because there's more of you, so your weight goes up. So how do we kind of get around this problem? The reason this is a problem is because essentially it kind of weakens the correlations. It might accidentally raise a correlation too high. It might lower one beyond what it normally is. It really depends on the experiment, but it just skews the data. It's not great. So it's good to look for those variables. There's two things we can do. We can choose to drop one. Let's just say we don't want to look at weight in the study. We just want to look at height. Perfect. There we go. Already done. And like if those are the only two variables, this would obviously become like single linear regression now, but that's, that's whatever. That's fine. Something else you could do for specific variables is if there's another equivalent, which in this case there is, you can actually combine variables. So if you remember, just from all our other classes, weight divided by height, not exactly in this form, can get us BMI. So instead of having weight and height, just use BMI. Again, if we get rid of both of those and just make BMI, that might become a single linear regression if that's the only variable. But yeah, that's just one way we can do that. So it's really being able to identify those variables. If you see something that's super related on the exam and he's asking like, which one could you get rid of? That's what he essentially wants you to do for that type of problem. So now let's go over some of the content I haven't really covered from Dr. Kim's recitation. Some of this is going to be a repeat, but in my last video, I did not include the recitation material, which turned out to be a mistake because I think I learned quite a bit in the recitation. There were a lot of concepts that were reinforced more. So I wanted to make sure to include it in this video. This first problem is a two-factor ANOVA problem. Or it's, yeah, it's two-factor ANOVA. In my notes, they said it can be ANCOVA. That's why I included it. That's right. So when looking at something like this on an exam, we could interpret this in a couple different ways. The way that Dr. Kim wanted us to interpret this was as a two-factor ANOVA, right? So in our columns and rows, we have these two drug treatments. We have vitamin D3 and omega fatty acids. And then the key is seeing or both here. So what we can do is when we fill something out like this, we got vitamin D3, omega-3, and then placebo. Right, standard two-factor ANOVA things. And we can fill in each of those conditions. And the reason you do something like this is to save money. However, I got this wrong yesterday in recitation. because I wasn't reading carefully. I didn't see that or both. You could interpret this in a different study as an ANCOVA, because you could look at cancer and cardiovascular disease being measured. So in this experiment, they're grouping these as one, right? These two different diseases are your dependent variable. If you remember though, or I'm sorry, you could interpret this as a MANOVA, not ANCOVA, in the sense that you are looking at two dependent variables, right? You could have cancer and CVD be your two dependent variables, and that's MANOVA, because remember, MANOVA has multiple independent and dependent variables. So just seeing that or both kind of indicates that there's going to be an overlap column between these two. So when you're looking at a table like this, you can instantly find out this is two-factor ANOVA just by doing that. So that could be helpful. Don't get tripped up on that in an exam. And that's honestly, like, he's probably not even going to ask us MANOVA questions, but, you know, just in case. Something else that I've kind of gone over, but it's that R values are not the same as P values. This table may look kind of confusing, right? These values might not look significant for a p-value of like 0.05, right? Because all of these are bigger than 0.05. It's because these are R values. So these are actually correlations. In this study, it's really important to read like this text. So you can see here that, or maybe you can see, it's very, very small. But next to this P, there is a subscript B, like floating above it. So anything with a subscript B is actually statistically significant. So you can see there's actually only one value in this entire table that is not significant, and that's this pre-pharmacy GPA and your ability to do the administrative sciences, so classes like fundamentals. So I think that's just really funny that even in the study that our school has done, that has shown up. But yeah, so R value not the same as P values. That's the big takeaway, because R values are correlations, P values are significant. Let me write that down because that's pretty important. R correlation. Hopefully I spelled that right. P significance. Something else is multiple linear regression may show what values in the table are significant as a p-value or an F ratio. The way they do this, the easiest way to read this is to like just draw a line across. Because obviously it's like we have more values. Essentially here, whenever there's a significant p-value or a significant F value, they're grouped together. So we can draw brackets. So here there's three conditions. So if we were to draw a line over from this normal saline, we can see that plasma warfarin is not, but warfarin clearance, draw a line. Oh look, that is. Same with vitamin K, non-significant, creatinine, non-significant, but for albumin, oh look, significant again. So just making sure, like drawing those lines, reading the table, it's so easy when the text is this small to mess something up like that. So don't mess that up if you can avoid it. Just draw your lines, you'll do better. And if it's on ExamSoft, well, maybe highlight if they let us. Otherwise, good luck, I suppose. So let's talk about some of the tests we've talked about so far. We will supposedly be learning all of these in our next video, which is a lot, honestly, because everything I have circled already is the test we've learned so far. So we've learned like t-test, z-test, ANOVAs, f-test, and we've also learned Spearman. I included that in here just because even though we briefly talked about it, Spearman's kind of like the equivalent of a Pearson coefficient for non-parametric data. But yeah, these are the tests we still have to learn. I don't really have too much to say about them other than this might be a good review. If you can recognize all the tests in this table, you're probably in pretty good shape, especially because he's not really going to have us do that much math on our own, I don't think. And then one more thing I wanted to point out is that most of our tests that we've learned so far will have one dependent variable. The exception to this is MANOVA, but since we don't need to do math on that, and canonical correlation, I guess. Because remember, these two are like similar in the fact that they have dependent variables. Look at that. I could have explained that so much easier than I did 3 slides ago. And most of our tests also only have one independent variable. Exceptions are two-way ANOVA, right? When we create a table like this, there's obviously two. Linear regression can have two or more. That's pretty much all I have to say about that. Good luck on learning this material. I will post the next part on Tuesday.